me, what were we doing in the last class?
That Dirichlet condition and Newman condition.
Excuse me?
Dirichlet condition and Newman condition. Boundary.
Just check. So who was it who was trying to tell that there is a GC class? How many attendance does he have in mathematical physics? Yes. Was it one of you? No? Okay, maybe the intelligent views. Alright. So, in yesterday's class, we were learning about a particular type of functions that we call particular type of operators that we call the self-adjoint operators. Yes? And we had seen that a differential operator, which in general is written as P naught d2 by dx2 plus P1, okay, P naught of x plus P1 of x d by dx plus P2 of x. This differential operator will be a self-adjoint operator provided what was the condition for it to be a self-adjoint operator?
Sir, P1x equals to dp0 dx.
Yes. The condition was that d by dx of P naught x should be equal to P1 of x. Okay. So if this is the condition, then the operator is a self-adjoint operator also with appropriate boundary conditions. Okay. Because for a particular second order linear differential equation, there needs to be a set of boundary conditions. So if the boundary conditions are appropriate, then this operator can be a self-adjoint operator provided this is true. Yes. Are you all okay with this? Tell me.
Yes, sir.
Yes, is that okay with all of you?
Sir, can you please?
Can I repeat?
In last class, sir, my internet got disconnected, sir. Last moment, sir. 10-15 minutes, sir.
एक बार फिर से बोलिएगा बच्चे. I could
Sir,
not get you.
Sir, in last class, my internet got disconnected, sir, for 10 or 15 minutes.
Okay, so then you pay some money. Because you did not pay the money to the internet company, right? That is why it got disconnected. So you pay some money to your friend and ask about the last class. Okay?
Okay, sir.
Or maybe you can get a recorded meeting. It is lying somewhere on my computer. Okay, but this was the condition. Is it clear to the people who attended my last class?
Yes, sir.
Yes? Okay, so to the person whose internet connection was low, you just try putting instead of P1x, you just try putting d by dx of P naught x. And then you see what is the nature of this operator. So what you will find is that if you have an inner product of P and and then this L operator acting on U, where P and U are the eigenfunctions of this operator, then you will find that this is nothing but LP of U. Okay? In general, this is not the case. Okay? But if this condition is true, that means if instead of this P1x can be replaced by this dy dx of P0x, and then you try to get what is the left hand side, then you will find that this left hand side is nothing but the right hand side over here. And if it is the right hand side, then in that case this L operator is said to be a self-adjoint or Hermitian operator. What is the second property of the Hermitian operators? Eigenfunctions of a self-adjoint operator. What kind of set do they make? If an operator is a self-adjoint operator, then the eigenfunctions of that operator, what is the condition on the eigenfunctions of an adjoint operator? Shabas? Batao?
Sir, eigenfunctions corresponding to different eigenvalues are orthogonal.
Are orthogonal, yes. They form an orthogonal set. कहने का क्या मतलब हुआ बच्चे? That if Q and V are two independent eigenvectors of L, then UV dx, UV dx. Okay, this is equal to 0. This is not the property of something. This is the property of the self-adjoint operator. Self-adjoint operator का क्या property होता है आपका? Self-adjoint operator का property होता है आपका that if there are two eigenfunctions, that means if there are two functions which satisfy the operator, okay, and they are two independent functions, that means they have different eigenvalues, then those eigenfunctions, they are orthogonal, orthonormal, or orthogonal to one another. Are you happy with this? Yes?
Yes, sir.
Yes. So if we can somehow prove that, okay, now I raise. So now, if you can somehow prove that what were these different functions that we were doing? That L Hermitian, L Basels, L Legendre, and L Lagarde. If these operators turn out to be, let us say, self-adjoint operators, enough. If they turn out to be self-adjoint operators, then we can confidently say that the eigen vectors corresponding to these operators, they will form an orthogonal set. So what are the eigenvalues or eigenoperators of Legendre operator? The eigenoperators of Legendre operators are these PL of x. है बच्चे? क्या होते हैं आपके लीजेंडर ऑपरेटर का आइगन फंक्शन? दे आर द PL of x. So if PL of x are the eigenoperators of Legendre are the eigenfunctions of the Legendre operator, and if Legendre operator is a self-adjoint operator, then these PLX will be orthogonal. Okay, I once again repeat. What do I say? I say that, okay, I will tell you what is the, you will yourself see what is the Legendre operator. I will just ask you in a minute and then you will tell me what is Legendre operator. Similarly, you can tell what is a Hermitian operator, what is not Hermitian. This was Hermite. You can similarly tell me what is a Hermite differential operator. You can similarly tell me what is a Bessel differential operator and a Lagarde differential operator. Our aim for this class will be that all these operators can be set to represent self-adjoint operator. हमारा aim क्या होगा आज के क्लास का? हमारा aim यही होगा बच्चे that all these operators are self-adjoint operators. Or if they are not, then some adjustments can be made to make them self-adjoint operators. है ना? Okay, let us see. Okay, हम इसके बारे में अभी थोड़ी सी देर में बात करेंगे. But if this is true, that means if this comes out to be self-adjoint operator, then and if PLX then we know is the eigenfunction of this Legendre operator. Then Legendre operator acting on the PL of x. This will give you, what will it give you? This will give you a set of orthogonal eigenvectors. That means this will imply that PLX, PMX with L not equal to M will be equal to 0. है ना? Similarly, H and X are the eigenfunctions of this operator. So if this operator turns out to be a self-adjoint operator, then HNX, HMX along with some weight factor, that will be the
0.
that will be the that will form an orthogonal set. Okay? Okay. Before doing this, let us check one more thing. And the thing we check is that let us say we have a differential equation, and in that equation our operator is, hold on students. So we would have a differential operator L such that it is P naught x d2 by dx2 plus P1 of x d by dx plus P2 of x. And in this, let P1 of x is not equal to d by dx of P naught of x. question, then is it feasible that this operator can be changed to some L dash? That means some L dash can be formed using this L so that this is self-adjoint. What is the question? So if this was equal to this, then we know that L is self-adjoint. Okay? What do we know? That if P1x is equal to d by dx of P naught x, then we know that L is self-adjoint. But let us for the moment assume that this is not true. You know? Then we would like to know that is there a way in which we can make a non-self-adjoint operator turn into a self-adjoint operator? And the answer is yes. So, what is the problem? The problem is that we want to turn a non-self-adjoint operator to a self-adjoint operator. And the way it is done is via some weight functions. Okay? It says that if L is not a self-adjoint operator, then L dash, which is some Wx times L, it can be a self-adjoint operator. So the question is, what is this W? So what is the question? The question is that if you can make this non-self-adjoint operator turn into a self-adjoint operator, then what is the weight factor? Let us just calculate this. So in order to calculate this W, so if this condition is true, if this condition is yes, then this W of x is equal to 1. Because in that case, L dash is same as L. You know? However, if this condition is not true, okay, then also we can make a self-adjoint operator from this non-self-adjoint operator. And the way we do this is that we say that let L dash be the self-adjoint operator. So if L dash is the self-adjoint operator, then L dash we know will be equal to W. W and then W over here. What will be L dash? L dash will be equal to what happened to this pen? Look, I asked some people. Some people. Yeah, this looks fine now. Yes, this is fine. Sorry. No, this is my house. Sorry. ओके सो हमने क्या किया बच्चे हमने L से फिर क्या कर दिया L was not a self-adjoint operator so we need L dash from this L by multiplying this L by a term which is W. Okay, so now you can calculate what that W will be. So L was not a self-adjoint operator. L dash is a self-adjoint operator. So if L dash is a self-adjoint operator, then we know that the coefficient of d by dx, which is W P1 of x. This must be the dy dx of the coefficient of this. है ना बच्चे? बताइए हमने क्या स्टार्ट किया है, क्या अज्यूम किया है हमने? We assume that L was not a self-adjoint operator, but L dash is. And the way we obtained L dash was just simply multiplying L by W of x. W of x is called some weight function. So we want to know what should be the appropriate weight function which, when we multiply it with a second order differential operator, with a general second order differential operator, turns that operator into self-adjoint operator. Okay, so let us see. So we multiply W over here and then we obtained this. So now our job is to find what W is. So इसको आप कैसे कर सकते हैं बच्चे? आप इसको कर सकते हैं that you can multiply this by P naught x and then also divide it by a P naught of x. क्या कर सकते हैं आप? From this was the condition. Wx P1x was the condition for this to be self-adjoint. That condition we put. That condition we multiply and divide it by this. Okay. These two terms from here they come to the left hand side. So the left hand side then becomes 1 by Wp naught into Wp naught dash. That becomes equal to P1 divided by P naught. Are you all following me?
Yes, sir.
Yes. So this 1 by Wp naught into d by dx of Wp naught by dx. This is equal to P1x by P naught. What is our aim? Our aim is to find what W is. Okay. So now this is 1 by some capital F and then d by dx of that capital F. This whole thing you know will be equal to d by dx of logarithm of F. Yes? Shabas? This will be equal to d by dx of logarithm of W of P naught. Do you all agree that 1 by Wp naught d by dx of Wp naught will be equal to this?
Yes, sir.
Yes, sir.
Shabas. So this will be equal to P1 of x by P naught of x. है ना? This differentiation can be turned into the integration of the other side. That means take integration of both sides. So if you take appropriate integration of both sides, then this implies that logarithm of W of x times P naught of x is equal to integration up to some x of P1 x dash by P naught x dash dx dash. है ना बच्चे? हमने क्या किया, इस dx को हम यहाँ पे लेके चले गए, है ना? And since this is an integral, so this x can be written as x dash because now this integral is over x. Is it clear?
Yes, sir.
Yes, sir.
Yes. But so this can further be written as that logarithm from the left hand side can be removed by taking an exponential of the right hand side. If logarithm of f is equal to c, this implies f is equal to exponential of c. Okay, because logarithm of the exponential is equal to 1. So this implies that this quantity whose logarithm was to be taken, which is wx of p naught x, this is equal to exponential of integration of p1 x dash by p naught x dash. But this is dash. This is not differential. Okay. This is just dash. Dx dash. And then what is w of x? W of x is equal to 1 by p naught of x. Okay. So a general second order differential operator can be converted to a self-adjoint operator via this function. This function is called the weight function for that operator. And then it says that if u and p are two eigenfunctions for the operator L, okay, which to begin with was self-adjoint, and then that L was made self-adjoint by this W. Okay, then if u and p are the eigenfunctions of the operator L, then u, v, and multiplied with W, W dx, that will be equal to 0, where u and v are two independent eigenfunctions of the operator L. Okay, देखिए पिछली बार हमने क्या लिखा था, PLX PMX dx is equal to 0, है ना? That was because in that case W was some constant factor, was not a function of x. Okay, but sometimes you will find that this W is also some factor which has been written with HNX, HMX. Especially जब आप when you are doing your exercise, when I think your assignment, and you come across these orthogonality relations for different polynomials, then you will find that in addition to HNX, HMX, there is some exponential factors also which are sitting besides that. Then you might worry as to how do those exponential factors come into picture. Those exponential factors come into picture because of the fact that this W in that case comes out to be a function of x. आपको समझ में आया?
Yes, sir.
Yes? You understand this now, right? This
Yes, sir.
happens when L explicitly is not an self-adjoint operator. Because if an operator is not a self-adjoint operator, then its eigenfunctions, they do not form an orthogonal set. No? It is only when that operator becomes a self-adjoint operator. So that self-adjointedness we know comes via multiplication of that operator with a function W of x. And what is the W of x? W of x is equal to this. Okay. So this way of converting the operator to the self-adjoint operator leads to now this self-adjoint operator's eigenfunctions. They will be the eigenfunctions which will form a orthonormal set, and that is the relation that we get. Okay, is that okay with everyone?
Yes, sir.
Yes. Tell me.
Yes, sir.
Yes, Shabazz. Okay, so all these things. Okay, there were certain conditions that I had given yesterday for the P notes, P1s and P2s. I think I had sent some class notes on your WhatsApp group as to what should be. So we have written this P
No,
note
sir.
as P, P1 as Q and this P2 as R. Okay, so I had given you certain conditions as to what should be P note, what should be P, Q and R and what should be the conditions that they should follow in order that that operator can be changed to a self-adjoint operator. A differential equation system involving a self-adjoint operator is also known as a Sturm Liouville system of equations. है ना? क्या बोला जाता है? A differential equation whose operator is either a self-adjoint operator or can be assumed or can be converted to be a self-adjoint operator. Those equations are said to represent something known as Sturm-Liouville systems. And we say, so then if these operators are also called Sturm-Liouville operators. And the set of eigenfunctions of these Sturm-Liouville operators, they form an orthonormal set. Okay, so without doing all these calculations that we have done, by which we have explicitly proved that they really are orthogonal to one another. Without this also, just by proving that the equation that we had, that was a Sturm-Liouville equation, we could have directly proved that the eigenfunctions corresponding to those equations, they are orthonormal to one another. So there was no explicit need for me to have explained to you all the stuff that I did. I could just have started from the Sturm-Liouville system. Sturm-Liouville system, I could have told that this operator has to be a self-adjoint operator. If this is not a self-adjoint operator, then by multiplying this factor, the operator can be made to be a self-adjoint operator. And once the operator becomes a self-adjoint operator, then we know that the eigenfunctions of that operator, those things are orthogonal to one another. So in that case, we do not need to explicitly show that they are orthogonal, starting from their generating functions and so on.
Yes, sir.
Right? Because we already know that if an operator is self-adjoint or a Hermitian operator, then its eigenfunctions they are perpendicular to one another. Happy everyone?
Yes, sir.
Yes. Yes. The homework exercise that I give you today is find if the four differential operators, that means if the Legendre operator, the Bechdel operator, the Hermite operator and the Lagarde operator, if they are self-adjoint operator or not. I tell you the answer that they are. They either are or they can be converted. So if they either are or if they can be converted, then find W of x for all of them. Okay? So आप देखिए एक छोटा सा एग्जांपल हम लेते हैं जिसमें मैं आपको क्या लिखता हूँ एक लीजेंडर ऑपरेटर का मैं लिखता हूँ लीजेंडर ऑपरेटर का हमारा क्या इक्वेशन होता है बच्चे the equation for Legendre operator is what is it Legendre क्या होता है आपका this is 1 minus x square d2 by dx2 what is the second term minus 2x d by dx what is the third term minus, sorry, plus L into L plus 1. That's it. है ना? बोलिए बोलिए. This
Yes,
is
sir.
the linear differential operator. You tell me whether it is or can it be converted to a, please enter to a, what is it?
Self-adjoint.
Self-adjoint operator. Tell me.
Yes, sir. It's
What is
already
self-adjoint operator?
Sir, it is already, I
It's
guess,
already a self-adjoint
self-adjoint
operator.
operator.
So, what is Wx for this? Wx for this is equal to 1. है ना? Why is it in self-adjoint operator? Because P1x, what is P1x in this case? P1x in this case is minus 2 of x. And what is P naught x? P naught x in this case is 1 minus x square. So this implies that P naught x dash, which is d by dx of 1 minus x square, this is equal to minus 2x. This is already equal to P1 of x. है ना? So this equation is already containing an operator that is self-adjoint. So we know, then after this we know that PL of x is a set of functions which are eigenfunctions of this. है ना? So then from here we can say that integration PL of x, Pm of x, where L and M are different, times W of x. W of x is equal to 1, dx is equal to 0. If L and M are different. If L and M are not different, then they are something like delta Lm times some Cm. Are you all liking this?
Yes, sir.
Yes, sir. Yes, sir.
yes, sir.
Very good. So this was a very important lesson to be learned from the Sturm-Liouville system of equations. Okay, there might be certain cases in which W of x does not exist. For example, suppose this 1 by P naught x is such P naught x is such that 1 by P naught x is not defined within the interval, let us say. Okay, so then then this W of x cannot be defined. Okay, in that case, that system of equation cannot be converted to a, that operator cannot be converted to be a self-adjoint operator. Okay, so that means those systems are not Sturm-Liouville system of equations.
सर मतलब जो नॉन एसेंशियली सिंगुलर होता है सर नॉन एसेंशियल सिंगुलरिटी सर नॉन एसेंशियल
What? Non-essential singularity, yes. Essential and non-essential. So if there is a non-essential singularity, that can be removed. Okay, if there is essential singularity in this equation, then that essential singularity cannot be removed, because essential singularity is a pole of infinite order. है ना?
यस सर
यही होता है आपका?
यस सर
Yes. So if there is an essential singularity in the equation, then that equation cannot be converted to a self-adjoint form. That cannot be converted to a Sturm-Liouville form. Okay. So we stop the discussion about Sturm-Liouville nature of the differential equation at this point. And now, in the remaining 5 or 10 minutes that we have, we discuss the last topic for the day, which is Wronskian. Okay, can I erase all of this?
Yes, sir.
Any question in this?
No, sir.
No? Okay, good. Very good. Okay, so the last topic that we discuss for the day is something that is known as Wronskian. Wronskian of a differential equation tells you about the dependence or independence of a set of solutions, a set of eigenfunctions. That's it. Okay. So, what is the meaning of the Wronskian? So, first thing is, what is a Wronskian? Wronskian is a tool, essentially. Okay. So, what it says is that, let us say, for a let us say Qx and Vx are two solutions. Of a differential equation. Okay, second order ordinary differential equation. Was it dynamic? There is a second order. Ah, sorry. It says that Ux and Vx. So, for example, Ux could have been like P1x, Vx could have been like P3x, or P2x, or P5x, or P4x, or maybe P1x itself. Yeah. It says that they are the solution. They are two solutions of, let us say, some second order ordinary differential equation. Yeah. We want to know whether these two solutions are, whether they form a independent set of solutions or whether they are dependent, they are linearly dependent. That means one can be formed from the other. So, for this, what you do is that you calculate something known as Wronskian for this, capital W. And the way this Wronskian is defined is, it is defined via a determinant. So, its determinant is that you write U function, second element that you write is V, which is the second function. Okay? And then you write a U dash over here and a V dash over here. And then you calculate the determinant of this. That means what is the answer? This implies W of x, oh, capital W, I'm sorry, Wronskian. Will be equal to U V dash minus V U dash. Okay? Why? Because this is defined. This is the definition. Its definition is that it is defined as the what is it?
Determinant.
Determinant of the solutions and their differentials. Then it says this will be W of x. Now there could be two conditions only. One could be that this is equal to 0, another is that it is not equal to 0. क्या हो सकता है W of x के साथ? W of x can only have two conditions. That one is that W is not equal to 0 and another is that it is equal to 0. If W is equal to 0, this implies that U and V are dependent solutions. And if they are not, then that means U and V are independent solutions of the second order differential equation. I give you some example to try, please. So you write a differential equation such that V double dash plus lambda V is equal to 0. Okay, hold on. No. Okay, this is true for Sturm Liouville system only. जो ये Wronskian है स्टर्म ल्यूविल सिस्टम के लेट अस से हमारा कोई स्टर्म ल्यूविल सिस्टम ऑफ इक्वेशंस है, उसके लिए हमने Wronskian निकाला है, एंड देन उसके बाद हम चेक करना चाहते हैं whether उसके जो दो सॉल्यूशंस है which are ux and vx, whether those solutions are linearly dependent or are they linearly independent. Okay, so in order to check the linear dependence or independence of any two functions, okay, what we do is we find the determinants of the functions in the first row and their and their differentials in the second row. Okay, this comes out to be this. If this is equal to 0, then they are dependent. If this is not this, then they are independent. Okay, you can take any two functions and check. You can assume that this function number 1 is the solution of this equation, function number 2 is also the solution of this equation. Then you can check whether those solutions are whether they are linearly dependent or not. For example, let us say u of x is equal to let us say 9x square, and v of x is let us say some 3x. Yeah? You can check whether this and this are linearly dependent or not. Yeah? So how would you check it? You will write it as 9x square, 3x, then this you will write as 18x, and this you will write as 3. So this is equal to 9 3s are 27. 27x square minus 54x square, which is equal to minus 27x square. So unless x is equal to 0, this is not equal to 0. Okay, so if x is not equal to 0, then these two solutions are linearly independent. But if x is equal to 0, then the one can be from the other. Can you check? Yes. Another situation could have been 9x instead of 9x square. So in that case, this wx could have been 9x, 3x, 9 and 3. And you calculate the determinant. So this is like 9x into 3 is 27x. 27x minus 27x. This is equal to 0. So since the determinant is equal to 0, since the Wronskian of these two functions is equal to 0, that implies that the two solutions ux and vx, they are linearly dependent. That means one can be formed from the other. So you know that ux can be formed from the vx by just multiplying a constant factor. In the other case, when it was 9x square, ux cannot be formed from vx via multiplication of some constant factor. Are you getting me? Yes. Tell me.
Yes, sir.
Yes, sir.
All of you. Yes. So if that makes sense with all of you, then what we can do is that we can stop the recording of this meeting. And I don't know how to stop the recording of this meeting because my computer has died. So just hold on. Okay, so until the time the computer switches on and I can formally switch off this meeting, what I tell you is that we have finished unit discussion on unit number 1 and unit number 2 of your syllabus of mathematical methods in physics. And now what we will do is that from the next class, which we will have next week, from the next class we shall start with the unit on Fourier transforms, okay, with Fourier series and Fourier transformation. Okay, so what is the day today?
Friday.
How many classes are expected in this month? Yes, can you please tell me? How many classes do we expect to have this? What is this? This is the month of June, right? So this will have 30 days. When is our next class?
Seven total 7 class.
Or total
Three
7 classes this week, is it?
3 week and additional Wednesday.
No, when is our next class? Which day is our next class? When is Monday? No, sorry, when is next Wednesday? Why don't you tell me? Why are you
9 9
9?
June.
Oh, okay. So we have lost a week, right? Okay, so 9, 10, then 16, 17, and then 23, 24, and then 30. Oh, okay. So 7 more classes. We will try to see. I think the unit should be over by the end of June. You know? And yes, then that will imply that we are on track. Okay. And if you people cooperate, then we will try to see if we can finish the unit a little early also. Okay, but that will depend on the cooperation, and I hope that you will be ready to cooperate in that case. So I am now stopping the recording of the meeting, and I will request if there is some question, then you please ask.